Welcome to my Financial Cryptography and Data Security 2025 talk. And this talk is going to be about whether compilers break constant time guarantees. So to reason about what constant time is and why it's actually useful, we first have to talk about side channel attacks. And so what are side channel attacks? So side channel attacks are a class of attack that uses implicit information. This can be, for example, a pattern of memory accesses or a pattern of branch directions, or also other stuff like sound or electromagnetic emanations to deduct secret data. And we basically have this algorithm on the one side with these emanations, which we here illustrated this box, and then an attacker comes along, and this attacker then uses statistical methods to, in the end, recover information about the secret that is processed by this algorithm from these emanations. And this is basically what a side channel attack is. And side channel attacks that I'm going to talk about in this presentation are mainly based on data access patterns and branch patterns of code. And how do we mitigate such side channel attacks? A common technique to mitigate them on a source code level is called constant time programming. And constant time programming basically eliminates all these emanations that source code could produce by changing the source code itself. And how could this look like? If we, for example, look at a very classic example which implements the maximum of two numbers, which we here consider to be secret, we can rewrite this code so that it doesn't contain the branch anymore. And this is what this rewrite would look like. And you now observe that basically this branch that you have on the left side, which would leak which of the two numbers would be bigger, which can, if this code is used in a cryptographic scenario, be a significant leakage that we want to get rid of, is now reduced on the right side or completely eliminated, because you don't have a branch anymore and you also don't have secret dependent memory accesses, so your code should be side channel free. But the question is now, with this technique, what can go wrong? And it turns out a lot can go wrong, because in reality we use compilers, and compilers like LLVM, which is illustrated here, can transform such properties such as data obliviousness of our code. So if we look at how code is basically executed, we start with source code here in C. This source code then classically gets compiled, and the compiled source code then is some form of assembly or bytecode in reality, but here for more easily readability we've illustrated it is as assembly. And this assembly then gets executed in a processor, which also produces the side channel. And on the one hand, we have constant time programming on the source code level, and the other side, we have the side channels on the processor level. In between, we have the entire compilation process, which is unaware of the existence of such abstract things such as constant time programming and side channels. The compiler basically only compiles to keep the semantic properties of the program, which can change independent, or which stay the same independent of the side channel properties of the program. So a compiler would be free to, instead of compiling this max operation on the left to a conditional move, to compile it to a jump operation. So this is basically a very straightforward translation of this left jump, and this would obviously have a side channel because we jump to two different locations depending on the result of the comparison. So we see that a compiler is basically free to transform our code into side channel secure or insecure code while still keeping its semantic properties. And the research question that now evolved from this are, how can we test for this generically? How common is this in representative source code, so cryptographic libraries or source code that processes secrets and wants to be data oblivious? And lastly, is there any interesting test properties that we can extend this with? Did we cover everything with basic tests, or can we extend our testing methodology? And first we're gonna answer the question, how can we test this generically? And for this we developed a testing pipeline where we have select source code samples that we used in our evaluation that get compiled with a lot of compilers and also under a lot of different compiler flags. And then we use not one but multiple testing tools for redundancy to basically test these source code samples under different inputs, again, for their data obliviousness. And in the end, we perform result analysis and cluster these results and see whether we can find any trends in optimizations breaking or fixing data obliviousness. And so let's start with the source code snippets. So we wanted source code that is representative of data oblivious programming. So we chose 4 sets of source code snippets that all process secret data and were either intended to be data oblivious or at least have very, very good reasons to be implemented in a data oblivious fashion. And in the beginning, we selected 9 small source code building blocks that are either known from previous literature on constant time programming, so they were like proposed online to basically be implemented in that way, or they stem from other papers that investigate the discipline of constant time programming. And for each of these small code building blocks, we proposed a constant time and a non-constant time version. So you basically now, for these code building blocks, have a reference where you know this should be constant time or this should not be constant time, also backed up by previous literature. Secondly, we also tested a constant time building block library. This library is basically intended to be used in your projects if you need special operations that are implemented in a constant time fashion. Lastly, or close to last, we checked the NIST lightweight cryptography finalists, because this is a new set of untested source code, new algorithms that have not been checked yet. And lastly, we used 5 widely used cryptographic libraries, as they all basically implement to some extent data oblivious programming and should be programmed in a data oblivious way. For the compilers, we checked 6 compilers in total, 4 of which were LLVM based, which is interesting because they share much of their source code but add different optimizations on top that could break data obliviousness. One of these compilers is formally verified, which is ComCert. And we tested for all these compilers all major optimization flags. So while all of these compilers have a lot more specific flags that you could potentially test, this quickly gets out of, this quickly scales badly, and you will not be able to test all of the individual flags. So we set it for all major optimization flags. And we additionally included one very interesting flag in ComCert, the formally verified compiler, which is there to reduce branches and should, in theory, be very useful for data oblivious programming. But it turned out in the end that this flag did not induce any significant changes. For the testing tools, we looked at 4 different testing tools with 4 different testing strategies. And basically we choose testing tools in ascending order of complexity, so that we can basically start with heuristic and fast tests, and then basically when these tests don't show that the binary don't show a clear result, we basically ascend to the next more complex test. And so the simplest test that we used was DUDECT, which is a dynamic timing based test that basically records the timing of the program under different inputs, and then does a statistical test on these timings that the program produces. And if these timings are sufficiently different, then DUDECT flags the program as non-constant time. If they are sufficiently close, then DUDECT says that the program is constant time. This is a very simple and easy to implement method of testing, we found out that this was quite effective, but also very much dominated by the execution time of the program, which could make it slower than the other methods in some scenarios. Secondly, we looked at data, which is a trace-based program which records the branch and data access traces of a program and then compares these traces under different inputs to each other. And if they are significantly different, then data flags something as non-data oblivious. And data we picked out of these classes of testing tools because it's quite mature and there's already a lot of previous work on it. Then we also chose CT-grind, which is also a dynamic tool that runs the program under many different inputs, but it uses taint tracking, which is different to trace-based tracking, as taint tracking basically starts from the secret value and then propagates some information which is called taint through the program. And then on any branch or any memory access, it can decide, well, is this tainted? Is it secret? If yes, then I can stop the program and basically say, well, here you're doing a branch on a secret value which should be forbidden. So taint tracking is a little bit more powerful than trace-based analysis, and we go into the details of when trace-based analysis fails and when taint tracking shines in our paper. And lastly, we also included symbolic execution with the pitchfork tool, which is quite different from the other approaches in that it is able to explore the entire program and will explore the entire program symbolically, and then in the end be able to prove to you that your program either has a violation, or if it terminates without finding a violation, it also proves to you that your program is data oblivious, which the other testing tools are not able to do. So basically, if you look in our pipelines, we test from simple to increasingly complex. And if we basically finish with symbolic execution and we don't find anything, we've proven at this point that the binary under test under the specific compiler option is data oblivious, which is also a very nice result. And also, this testing pipeline allows to retest previous violations for more confidence. So for example, DUDECT, due to its timing-based nature, could, under some very rare circumstances, give you a false positive, which you could then eliminate by retesting with something that is trace or taint backing based, or even with symbolic execution. So after I've introduced our testing pipeline, we basically arrive at this question of how common is this behavior? And for this, we basically ran our evaluation over multiple weeks on all these libraries and all these different testing tools, all the different compilers, and evaluated the results. And for more detailed, in-depth results for the specific libraries, I would redirect you to our paper. But I'm going to talk about these code snippets that were specifically designed because they were appearing in previous work, or we found them very interesting and relevant to data oblivious programming. And these are basically the results of the tests with these small code snippets. And what you can see basically is here a big table where we on the left have the name of the snippet, on the top have the compiler and optimization level. And if you see a cross there, the binary is non-data oblivious, so it has a violation, it's vulnerable. The color of the cross indicates which tool found it. And in the end, if you have nothing there, you see that the binary is data oblivious. And for example, what is very interesting is the third line from top, where you have Clang, AUCC, and ICX, which are all LLVM-based compilers from the LLVM project, AMD and Intel respectively. And we see that for this fixed lookup table example, they all produce different results, even though they're all based on LLVM internally. So you can see, even though much of these compilers overlap, you can still see optimization level dependent effects. And this is also true for other examples. So in general, to sum up this table, compiler and optimization level dependent effects exist. And we basically looked at these effects over all the code snippets, and we found that all directions of changes existed. So we had source code, which was intended to be data oblivious, which got optimized into vulnerable binaries. We also had the other direction, where we had source code where we intuitively would say, this is something that should be, if you naively compile it, should be vulnerable, but then this got optimized away into something that is data oblivious. All the compilers that we looked at have this optimization level dependent behavior. And there was sadly no clear winner in terms of compiler options, and also no clear winner in terms of compilers. So there's no clear recommendation on if you want the most data oblivious code, use these options and these compilers. This sadly very much depends on the nature of the source code that you're compiling. However, we showed that with testing, it is definitely always possible to find a configuration if you have reasonable source code that leads to data oblivious code. And the good news is also that we analyzed this constant time building block library, and this constant time building block library stayed constant time everywhere under all the options. So this shows that there's methods to write very robust code even in the presence of a ton of different compilers and a ton of different optimization strategies. So this gives hope for developing constant time code that is robust to compilation. So in the end, we asked the question, are there any tests we missed? Are there any interesting properties that we could add to existing tools that are very much necessary nowadays? And so we identified a few core things that we looked at. And first of all are variable time instructions. So if you, for example, have a division or something like this, this can take, depending on the operands, a different amount of time. And in recent times now, there have been a few papers that analyzed such instructions, and that also showed it is possible to build a text based on these variable time instructions. And so testing for them makes a lot of sense, but more sophisticated tools that do not rely on only the timing of the binary basically generate a branch and data access trace, and these traces do not include special instructions. So you would have to modify the tool for supporting variable time instructions, which is kind of a lot of effort, especially if you want to test with multiple tools. Then you also could want to test speculative constant time, which is something that has also seen a lot of interest in other research. So under speculation, basically your program could access program paths that previously were not valid because they are speculatively executed and guarded behind a branch that is architecturally never taken. Nevertheless, you can still encode data in these paths into the cache and leak data. So speculative, like constant time under speculation, is a very interesting property if your processor is an out-of-order one, which most of the modern processors now are. Lastly, we also wanted to address scalability. So we asked the question, could you change the binary in any way that, for example, taint tracking or symbolic execution-based codes tools are more effective? And it turned out that this is not supported by current tools, and we basically, instead of modifying the tool, took another route for our idea and went to binary rewriting. And I'm going to explain this with the example of variable time instructions. If you are interested in, for example, constant time under speculation via binary rewriting, I would refer you to our paper. So for variable time instructions, what we did is we first performed an instruction leakage test, where we basically run an instruction with different operands as an input and different values for these operands, and then basically see, does that make any difference in the timing with a statistical test. Then you normally compile your binary, and then you rewrite this binary by replacing all these instructions that are flagged as not being data oblivious with a special trampoline that the code jumps to. And I'm going to explain what this trampoline does later. And then you can normally test with an unmodified constant time testing tool and find violations for variable time instructions. So how would we rewrite these things? So first of all, we used E9 Pietsch, which is a very mature tool that allows to rewrite binaries in place. And for each instruction that we tested as variable time, we added a trampoline that you unconditionally jump to, which adds data flow and control flow. So artificial data and control flow based on the operands. And existing tools now can detect operand-dependent leakage, because for every instruction, they anyways track whether the operands are secret or not. And if you add data and control flow that is secret dependent there, then you can use existing tools to basically detect this leakage for variable time instructions. And so this is how you do it for these variable time instructions. For speculation or for efficiency, you basically have different rewriting techniques that also lead to basically testing novel properties with existing tools. So to sum up, we basically observed that from source code to code execution, you can introduce side channels via compiler optimizations. We first motivated this with an example, and then we asked the question, how can we test for this generically? And to generically test, we developed a pipeline. We selected representative source code snippets, and we showed how to basically, with multiple testing tools, efficiently test for compiler optimization induced vulnerabilities there. Lastly, then we also asked how bad are these compiler transformations, and we basically showed that every compiler and many optimization flags can change data obliviousness in one or the other direction. And there's no clear winner in terms of compiler flags or compilers. And last but not least, we also integrated new test properties without requiring changes to existing testing tools by rewriting the binary, so that we were able to test variable time instructions, constant time under speculation, and increase the scalability of existing data obliviousness testing tools.